In this video, I want to look at the fact that the set of real numbers under its addition and multiplication forms a complete ordered field. I first of all want to start by making a note. It turns out that in the formal development of the real number system, we accept that R under plus and times satisfies the completeness axiom as an axiom of our reasoning system. In other words, we usually do not think in terms of trying to formally prove the completeness axiom works from the other axioms that the real numbers have to satisfy. But just because we're saying that the completeness axiom is going to be true by assumption doesn't mean that we don't want an intuitive rationale for accepting this axiom as an axiom. And that's really what we're going to be looking at in this particular video. So I want to kind of start with a real number line. So here's my real number line. And what I want to think about is why Q failed to be a complete ordered field. And when I think about this question, I'm going to realize that our basic model of the real numbers makes it reasonable to believe that the completeness axiom should hold. What I want to remind you of is that in the previous video, we defined the set X, S, to be the set of all x's inside the rational numbers such that x was bigger than 0 and x squared was less than 2. And what we found was that the fact that the square root of 2 is not in the rational number system is what caused the soup of S to not exist inside the rational numbers. In other words, one way of thinking about the rational numbers is that they're piling up here, but there is a hole in the model of the rational numbers at the square root of 2. In other words, if I tried to graph all of the rational numbers, yes, I know that there's an infinite number of them and they pile up everywhere, but the rational line is full of holes. There's a hole at every single irrational number. Irrational numbers don't belong to Q. And so if I were to graph them, I would also have holes everywhere. And that's what these open little dots are supposed to be indicating. So the graph of the rational numbers is a whole bunch of dots where I do have rational numbers and a whole bunch of holes where I have irrational numbers. Well, if I think about it, the holes are what causes the problems for Q in making Q not complete. And if I think about it even more carefully, R has no holes. If I look at a number line, no matter what point I pick, that point, which I'm going to call x, is always going to be a real number. And this point x would always be a real number. So let's call this one x1 and this one x2. And if I pick another one, this x will also be a real number. So if I'm thinking in terms of the fact that R has no holes, that's going to imply that if a set is bounded above, then there's going to have to be a soup for that set. So if a set S is bounded above, then soup S is basically going to happen where the upper bounds run out. And that will be a real number because there are no holes. So this will be inside of the real numbers because R has no holes. So in other words, what I want to be thinking in terms of is looking at a number line, and let's put some crazy stuff over here. Let's actually change the color. So let's make that a different color. So this crazy stuff over here is supposed to indicate all of the elements of S. But I also know that I clearly have an upper bound. Well, if I have an upper bound, I can slap a little delta ball around it. So this is my first upper bound. And I can ask the question, are there any elements in S that belong to this delta ball? And if the answer is no, then I'm going to simply say, okay, this is another upper bound. But if I do have elements, let's look at that picture. So let's suppose here's my U, and here's my delta ball. And I know that there is an S inside that delta ball. Well, again, I can think in terms of space. So the question is there any space in here? And if there is, I can repeat the argument. And so basically what I find is that I eventually figure out that I will find an upper bound that has the property that every delta ball contains at least one element of S. In other words, I get down to a number line that looks like this. Here is my magic upper bound, and I'm going to call this one U hat, and every single delta ball about U hat is going to contain at least one element of S. And then I look at a smaller one and I get another element of S. Well, what this basically means is that if A is less than U hat, then A cannot be an upper bound for set S. Well, what does that actually mean? That would mean that U hat is an upper bound, because remember, I was looking at things that are upper bounds, and U hat is the smallest upper bound, because nothing less than, and I want to write this out very carefully, because A less than U hat implies A is not an upper bound. So all of the upper bounds are at least as big as U hat. So all upper bounds are at least as big as U hat, and that's enough to say that U hat is indeed the soup of S. In other words, the whole fact that we have soups is based on the idea that the real number line has no holes. So Soups exist because the number line has no holes. And that's why we take it on faith. We take it as an axiom. So no holes means we take the completeness axiom as an axiom for the real number system. It's tantamount to saying there are no holes on the real number line.